Hello, today I will present my thesis, BIM connection recommendation based on machine learning using multimodal information. First, I will introduce the background of my thesis. What is BIM? BIM is short for Building Information Modeling, which is a digital representation of the structures, for example, the buildings and the bridges. Tekla Structures, also known as TS, is one of the most popular BIM softwares. In TS, the most basic element is part, such as the beams and the columns. The parts are connected by connections. Here we give some examples of the connections. They are categorized into different types. The problem of connection type finding in TS is that there is a wide range of connection types to choose from, which could be time-consuming and prone to human errors. This problem gives rise to the need of an accurate and efficient connection recommendation algorithm. There have been studies conducted at Trimble about this problem. They use attributes or images, and they all have the limitations, such as the limited scenarios, scalability, and also high computational cost. However, there's one common observation we can obtain from these studies, which is that similar connected parts will have similar connections. That is why we formulate the problem as a classification problem, where the labels are connection types and the train and testing data are the parts to be connected. Here comes the question. We have both the attributes and images. Which one should be used? Can we use both? The idea of using different sources of information for training is actually called multimodal learning in the field of machine learning. Some studies suggest that different modalities could convey complementary information, thus help us in some classification tasks. Therefore, we form our goals as twofold. First, for single modalities, we try to improve the accuracy and efficiency of the connection type classification based on existing methods. Second, we will do multimodality method exploration by applying the multimodal learning methods to the connection type classification problem using both the attributes and the images. Now let's look at the methods. For attributes, we use the metadata, which contains the geometry and material information, and the autoconnection data, which is calculated from the proximity and the orientation of the parts. Here we use the decision tree-based algorithm. In the previous studies, random forest has been used for assembly classification, and here we adapted for our connection type classification problem. And we further investigate another variation of decision tree algorithm, which is called XGBoost. For images, we collect the 3 views of the connected parts as a dataset. The dataset will be pre-processed by downscaling, grayscale conversion, and normalization. The pre-processed images will go through 3 phases of a CNN model. It will first go through this base model to extract the visual features. The size of the feature will be reduced by the feature reduction layer, which will then be classified. The base model we use here is called Mobile Net V2, which is a lightweight CNN model. Now we will look at the multimodal database methods. We mainly consider the data fusion methods. The first one is called late fusion. Late fusion trains the models for the single modality data separately and aggregate the prediction score in the final stage by taking the element-wise summation or maximization. In intermediate fusion, we use exactly the same model as we used in the image-based methods. The only difference is that we concatenate the metadata with the extracted visual features and form a visual representation layer before the classification. This layer is put into a softmax classifier to predict the final result. To evaluate our methods, we use the commonly used metrics for multi-class classification problem, including the top 1 and top 3 accuracy, the weighted F1 score, precision, and recall. We also measure the time spent on the training and testing as an indicator of the efficiency of the models. We have conducted 11 experiments of 5 categories, and in each experiment, we do nested cross-validation, which does the hyperparameter selection in the inner loop and performs the model performance evaluation in the outer loop. The results are collected on a dataset which consists of 1,731 connections of 12 types. First, we will look at the attributes-based method. So we compare the random forest with XGBoost on metadata. This table shows that XGBoost has better results than random forest, but the improvement is not very prominent. For the efficiency, XGBoost is slower than random forest in training, but faster in testing. And if we further look at the results on all the attribute datasets, we can find that this conclusion about the accuracy always hold, because if we look at the green line and dot, which represent the XGBoost method, is always higher than the blue line and dots, which is the random forest. For image-based methods, we will compare the existing and improved CNN on images. So for accuracy, the improved CNN is more accurate than existing CNN. We can see there is 5% improvement in top 1 accuracy. And the improved CNN has enhanced the speed of the training and testing by around 50%. Now we will look at the results from the multimodal data and compare it with single model results. The most prominent results is that XGBoost and the metadata outperforms other combinations. And if we check the orange boxes, the late fusion method follows the XGBoost method. It has slightly lower performance, but is still better than other methods. And if we look at the red boxes, we can say that the intermediate fusion has slightly improved the image-based methods, but also the improvement is very minor. In terms of the efficiency, XGBoost and metadata is much faster than other combinations. and the improved CNN is about 38% faster than intermediate fusion. This could be because the intermediate fusion includes the attributes, so it's slower in classification. Now let's discuss the reason behind. Why doesn't the multimodal data fusion improve the performance of attribute-based method? We will look at it from the two different methods. For late fusion, we can say that limited complementary information exists in the two different data sets. From the domain knowledge, we can actually see that attributes contain more information conveyed by images. Attributes have the geometry, material, and structural information, which has included the ones conveyed in images, like the relative size and the profile of the parts. If we further look at the confusion matrix, we can find that metadata and XGBoost performs better than image and improved CNN in terms of every class. So if we simply take the maximization or the summation, we can't really take advantage of the image-based method. Then why is also the case for the intermediate fusion? I think it is because of the dominance of images. So we can say that the results, the accuracy of these two experiments are quite close. This could be because that the images and the attributes features, they have different levels of abstraction. So when we do the classifications, the images will dominate the classification. And also the size of image features is larger than that of the attributes. This imbalance could cause the dominance of the images. Finally, we will conclude this work. Metadata and XGBoost yield the best results among all our experiments, and the improved CNN model has enhanced both accuracy and efficiency compared with the previous model. Also, the late fusion and intermediate fusion methods can't further improve the accuracy of connection type classification compared with the attribute-based methods. For future work, we plan to explore other representations, such as the point cloud, which is accurate and also fast according to related studies. We will also experiment with other multimodal learning methods. So, like different structure of the CNN model in intermediate fusion could be experimented. Thank you for listening.